Thank you. I'll just say this talk is not like the others. I am talking about cluster algebras, just cluster algebras. So first of all, I'm gonna avoid this hand actually because it's kind of laggy. So last week in the graduate workshop, we talked about Zamolodchikov periodicity, and cluster algebras were also talked about in the undergraduate workshop. So I feel very fortunate today to be able to discuss this topic to such well-educated pupils. The first thing is most people have heard about cluster algebras specifically in the context of quivers, which are in bijection with skew-symmetrizable matrices. These are natural bijection if you just take the adjacency matrix, but there are more than just quivers out there. So we say that a matrix is skew-symmetrizable if we can make it skew-symmetric by scaling its rows by some positive scalar. For example, this matrix here is skew-symmetric because we can scale its rows by 1, 3, and 2 to get to a skew-symmetric matrix on the left. And both of these generate a cluster algebra. In fact, every cluster algebra is generated by some skew-symmetrizable matrix. In terms of the Dynkin diagrams, these two categories split the Dynkin diagrams into their simply laced and non-simply laced types. You probably have seen these before. Sometimes we refer to these just as ADE Dynkin diagrams because that's literally what they are. You'll notice that I have colored these vertices black and white because they are all in fact bipartite. And this is going to be very important to the rest of the talk. From now on, we will only be talking about bipartite objects. So we say a bipartite matrix is recurrent if when we apply cluster mutation to all of the white vertices or all of the black vertices, the result is just reversing all orientations. Equivalently, we can write this matrix as a sum of two commuting matrices that are oriented in different directions. To such a matrix, we associate a T-system, which is an infinite family of variables that satisfy the following exchange relations. I've also written these exchange relations up here so that we never lose them. And finally, a bipartite recurrent matrix is Zamolodchikov periodic if its T-system is periodic.
What is the product?
What is the product over? It's over all indices. So if this is an n by n matrix, it's from 1 to n. Yep. So let's take a look at a very simple example, just 2 points and a single arrow. As our T-system progresses, we can see that our expressions get more and more complicated, but something magical happens right here, which is it becomes more simplified. And we do get back to our original cluster variables, our original state. The only difference is that our roles have been replaced. Our roles have been reversed. So now T1 is associated to X2, whereas T2 is associated to X1. So we can imagine if we do this 5 more times, they will switch back and we will get back to our original state. Some people may recognize that this is the cluster algebra of type A2. So for those people, I have drawn the triangulations for A2 that correspond to this progression. We start with a single triangulation, and we continue as we mutate. And every 2 steps, you notice that our triangulation rotates. And on step 5, we get back to our initial triangulation, but the lines have been reversed. Okay. So this magical phenomenon was first observed by a physicist named Zamolodchikov. He observed this for the ADE case. In his study related to conformal field theories for thermodynamics. And do not ask me anything more about that. But these were not fully proved until Fomin, who is right here, and Delevinski introduced cluster algebras and showed that this is in fact just a cluster algebra and this is cluster mutation. So they were able to show it not just for the simply laced types, but for all Dynkin diagrams. Next, we have Keller, who in his Annals paper generalized this result to all tensor products of Dynkin diagrams. So the question then became, what more is there? Are there more objects out there that are Zamolodchikov periodic? And in 2019, Galashin and Pawlowski classified every quiver that is Zamolodchikov periodic. So this is the end of a very nice story, but there is a little bit more to go because quivers are not everything, right? As we talked about, there is skew-symmetrizable matrices. So last fall, I classified all of these Zamolodchikov periodic cluster algebras, and these are in fact just pairs of commuting Cartan matrices. These make up 35 infinite families and 25 exceptional types. And these are just a few of those families. So on the left right here, we can see one of these eukaryotic quivers, and these are two of the non-quiver families. I've drawn some little arrows here that show two operations that do preserve Zamolodchikov periodicity. And it is true that you can get every single one of these 60 families from these eukaryotic quivers with just these two operations. Okay, but we know more than just we have a pair of commuting Cartan matrices. We know the period exactly, which is 2 times the sum of the Coxeter numbers. So this is the Coxeter number associated to gamma and the Coxeter number associated to delta. So one question I asked this year was, what happens if we remove this 2? Why is that so important? Is there still nice behavior at the half period? And there is. It is just a permutation of the cluster variables of order at most 2. And here is an example. If we take some quiver at the half period, the sum of the Coxeter numbers, all that has changed is that 8 and 9 have swapped places. And if we do it another 10 times, they will swap back. We can also see that in our A2 example, these just at the half period swapped places. Okay, so that was actually the end of all my results. So for my last slide, I wanted to talk a little bit about something I'm thinking about currently. We can tropicalize our system. And that just means I take product and turn it into addition. I take addition and I turn it into max. And depending on the evaluation of this max function, I can color the mutation either red or blue. So we can color it red if the gamma component was dominant, or we could color it blue if the delta component was dominant. And if we look at one full period in the T system and color everything, we notice something very interesting. Namely, the number of these gamma mutations is the same as the number of roots in the root systems associated to gamma, and same with delta. Moreover, due to the half periodicity result, this reduces down to just the behavior in one half period, which determines the entire system. So now we only need to show that the number of gamma mutations is the number of positive roots. So some people that attended the workshop last week might remember that there is more than the finite case. There are the linearizable families, which is the affine finite types, where one side is affine, one side is finite, and this conjecture still seems to hold for those families. We no longer have periodicity, but we still have the number of finite mutations still seems bounded by the number of positive roots. So just to briefly conclude, I think this is a very interesting connection. It shows that there's something unknown connecting root systems and these colored mutations, and potentially a very nice bijection between positive roots and cluster variables in the T system.
Time for one question.
Do you have a slide showing off the 35 families?
I have slides showing off like 20 of the families.
Okay, do we have math question? Right, if not, let's thank Ariana.